Imagine taking a blurry image and magically sharpening it, or detecting edges, or making AI understand patterns in sound, photos, and even your handwriting. Behind all of this is one quiet mathematical hero, the convolution. It powers modern AI, computer vision, audio processing, and more. The word convolution sounds intimidating, but the idea behind it is surprisingly intuitive. At its core, a convolution is a way of combining two sets of information, usually a large signal, like an image or audio track, and a smaller pattern, called a kernel or filter, to produce something new. It's like sliding a tiny magnifying glass over a big picture to see how well certain patterns match. That's it. That's the whole idea. Let's break it down step by step. Think of convolution as pattern detection. Imagine you have a giant wall of text and you want to find every place the word AI appears. You slide your eyes across the text, scanning for that pattern. A convolution does the same thing mathematically. A kernel, the pattern you're looking for, moves across the input, the data, and at each position it produces a score based on how similar they are. A high score indicates a strong match, while a low score signifies a weak match. This simple operation is the foundation of image processing, neural networks, and dozens of other systems. Let's break down the convolution process with a simple analogy. Let's say your input is a big grid of numbers, like an image where pixels are numbers. A kernel might be a smaller 2 by 2 grid. You place the kernel on the top left corner of the input, multiply overlapping numbers, add them up, and write the result into a new grid. Then you slide the kernel by one step, like moving a window, and repeat. That sliding, multiplying, and summing is the convolution. Why does this matter for images? Because images are full of patterns, edges, curves, textures, corners, shapes. Different kernels detect different patterns. A vertical edge kernel highlights vertical lines. A horizontal edge kernel highlights horizontal lines. A blur kernel softens details, and a sharpen kernel increases contrast. By applying the right kernel, you can completely transform an image. This is the origin of famous filters like edge detectors, sharpening filters, blur, and embossing. And these are exactly what convolutional neural networks, or CNNs, use under the hood. In neural networks, specifically CNNs, convolution is the operation that extracts features from images. Instead of manually crafting kernels like early image processing did, neural networks learn the kernels automatically. A CNN will learn kernels that detect edges, curves, textures, eyes, noses, wheels, leaves, and even entire objects. Layer by layer, these kernels evolve from simple low-level features like lines to complex high-level concepts like faces, animals, and objects. Convolution is why AI can recognize your face, read handwritten text, drive a car, detect diseases in medical scans, and classify plant species from a photo. It's probably one of the most important mathematical operations in modern AI. Images aren't the only signals that use convolution. Anytime you want to modify or analyze a signal, like a song, a heartbeat waveform, or a seismic vibration, you can use convolution. Here's what convolution does in signal processing. It creates echo or reverb by multiplying the signal by a kernel that represents the environment's reflection pattern. It performs noise reduction, where a smoothing kernel can block out high-frequency noise. And it enables pitch or tempo analysis, where kernels can detect repeating wave patterns. If you've ever used auto-tune, noise cancellation headphones, or audio equalizers, you were using convolution just without realizing it. Believe it or not, you already do convolution-like operations intuitively in everyday life. For example, searching through music, you hum a tune, the pattern, and try to match it in your memory, the signal. That is convolution. Another example, detecting a flavor in food. When you take a bite of a complex dish, your brain compares the taste pattern, the kernel, to known tastes, the input. Another convolution, finding a word in a paragraph. Your eyes scan across, checking small windows of text at a time. That sliding movement mimics convolution. The word comes from Latin volvere, meaning to roll. You can think of convolution as rolling one pattern across another. Mathematically, as the kernel moves, parts overlap and combine, or convolve. The size of the kernel matters. Small kernels, like 3 by 3, capture fine details. Large kernels, like 7 by 7 or 11 by 11, capture bigger structures. CNNs stack many small kernels instead of using one big one because it requires fewer computations, introduces nonlinearity, and creates deeper feature hierarchies. That's how things like ResNet and inception models work. When you learn convolution and deep learning, you'll see a few extra terms. Here are the simplest explanations. Stride refers to how many steps the kernel moves each time. Stride 1 moves 1 pixel each time, while stride 2 jumps 2 pixels, which is faster but captures less detail. Padding involves adding a border of zeros to the image so the output doesn't shrink. Filters or channels mean multiple kernels applied at once. More kernels equal richer understanding and more features. A convolution is simply a smart sliding comparison tool. It slides a small pattern over a large signal, measures similarity at each location, and produces a new transformed output. From sharpening photos to powering deep neural networks, convolution is everywhere. A convolution is a way of sliding a small pattern over a larger piece of data to detect features, transform signals, and extract meaning. And it's the backbone of modern AI and image and audio processing.